Right. And in this last section, we're going to go over some of the trends of the periodic table. As I told you before, there's a lot of information in this periodic table, and it's set up in a very particular way. So again, this is just another layer of information that we can get from the periodic table, from the way that it is set up. So the vocabulary in this one, it's actually a really short list, but we're just going to talk about how they fit into the periodic table and what each of these are, obviously. So they are electronegativity, atomic radius, and ionization energy. All right, so let's start with electronegativity. This is our first one. And so electronegativity is really just an atom's ability to draw electrons or to hold on to its electrons. So this will be a very, never mind. It's another way to think of it is just how greedy an atom is for electrons, how easily it can pick up new electrons, and how unlikely it is for them to give them away. All right, so this will be a very important factor when it comes to bonding. We'll look more into that in the next unit when we're talking about chemical bonds. But for now, we just need to remember that fluorine is the most electronegative element. If you're not too familiar with the periodic table for fluorine, it's over here in the top right. It is number 9, and it is the first of the halogens. So really, fluorine will always be the most electronegative atom. That's just the way that it works. And so without getting into the math for it, just remember that fluorine is the most electronegative element on the periodic table. And then opposite of that will be francium. Over in the opposite corner of it, this is the least electronegative element. And so just knowing these two pieces of information, we can draw a trend that anytime that we are over in the top right near fluorine, we know we will have a very electronegative element. And whenever we're in the bottom left near francium, we know we will have a not very electronegative element. And so if you are comparing two different elements on the periodic table and you want to say which one is more electronegative or less electronegative, just look at them and their placements relative to either francium or fluorine. I think it's easier to focus on fluorine because anytime that you're moving towards fluorine, you're increasing the electronegativity. So that's in two directions. If you're comparing two elements that are in the same column, if one of them is higher up on the periodic table, that means that it will be more electronegative. And if they're in the same group, in the same row, if whichever one is farthest to the right will be the most electronegative element of those two. So as an example on here, let's say that we're comparing sodium and magnesium. And you want to say which one of these has the most electronegativity. Well, just following this trend, remember that the one that is closest to fluorine on the right will be the most electronegative. So in this one, magnesium is closer to fluorine than sodium is. Magnesium is farther to the right, so magnesium will be your more electronegative atom. But now let's add potassium. Let's say we're comparing sodium and potassium. In this one, sodium would be more electronegative than potassium because, again, it's higher up on the periodic table. It's closer towards fluorine in terms of height. And then if you wanted to compare all these three together, well, you already know that magnesium is more electronegative than sodium, and sodium is more electronegative than potassium. So if you wanted to rank them in order of increasing electronegativity, you would have potassium first, sodium second, and magnesium third. Next, let's talk about the atomic radius. And so when we're talking about the radius of an atom, we're really just talking about the size of an atom. And so we measure this by the distance from the nucleus to the outer energy level. And this one is measured in nanometers. So we can see here that I have this chart of all these different atoms and their different sizes so that you can compare them all. And so what's going on here is that if we focus on lithium to sodium, notice that we're getting bigger along the way. So in lithium, we have an atom with 167 nanometers in size, and then we get sodium, which is slightly larger than that. It's 190 nanometers. And if we continue looking down, we have potassium at 243, rubidium 265, cesium 298. So you see that every time we go down on a group or an element family, we are getting slightly larger and larger atoms at every step. And so this is because when we look at the atomic models, we know we have different energy levels or different electron orbitals, shells. And so at every turn, at every new row, we are adding one more energy level. So if we look here at lithium, we see that it only has two energy levels for electrons. And if we compare it to sodium, which is the next one on the list, it will have three rings around it. So we have 1, 2, and 3 for sodium. And finally, for potassium, it will have 4 energy levels. So that's what the numbers on the side are telling us, that hydrogen will have 1 energy level, lithium has 2 energy levels, sodium has 3 energy levels, and everything in that row will also have 3 energy levels. All right, so just every time that we move on to the next row, we're adding 1 more energy level, and this is what's giving us a larger radius for our atom. So we can follow this trend if you're ever comparing 2 different elements, so say calcium and strontium. Because strontium is lower on the periodic table, we know we'll have a larger atomic radius, again, because it has more energy levels. Calcium only has 4, strontium will have 5. But then something interesting happens when you're comparing going across a row. We see that if we focus on hydrogen, here it has an atomic radius of 53, and go all the way across to helium, it will have an atomic radius of 31. So notice that when we have the larger atoms on the left side of the periodic table, and the smaller ones go on the right side of the atomic of the periodic table. And so it's a little bit odd when you think about how much stuff there is inside of each nucleus for these atoms. If we look at hydrogen, it only has 1 proton, and for helium, it has 2 protons. So you would think that having more protons in the nucleus, that it would make it a bigger atom. But no, what's actually happening is that the more protons we add to our nucleus, we're getting a stronger nuclear force. Remember that protons are the ones that are responsible for the nuclear force. So again, having more protons in that nucleus gives you a stronger nuclear force, and that stronger nuclear force actually has a compressing effect on our atomic radii. It makes it smaller because the nuclear force is so strong, it's pulling more strongly towards the center for each atom. So that's what we see, especially if we compare on this 4th group where we have a lot more atoms to look through. We can start with potassium. It has a radius of 243. Next, over to the right, we have calcium with 194. Scandium 184, and titanium 176. So you see that we're getting smaller and smaller as we go closer, as we move towards the right. So another way to think of that for our trend, if we are focusing on increasing atom size, is that if you start from the left side and you move, I said that wrong. If we start from the right side and we move towards the left, then we are increasing our atomic size. And if we start from the top and work our way down, we're also increasing the atomic size. So you could draw a big arrow going from our smallest atom, the helium atom, down to francium, actually. This graph, it's missing the 7th row. So there should still be another row below that, and would show that francium is our largest atom, not just cesium. So just anytime that you're starting in the top right and you're moving towards the bottom left, you're always increasing the atomic size. So if you're comparing 2 elements in the same column, the one that is lower down will have the largest atom. If you're comparing them across the row, the one that is farthest to the left will have the largest atom. And finally, we're moving into ionization energy. And so ionization energy, please remember that it's how much energy it takes to remove an electron from an atom. And so it's actually a very important property for chemical bonding. And again, we'll revisit this a little bit more in Unit 5. We'll go more into detail. But for now, notice that it goes a lot hand in hand with electronegativity. So as we talked with electronegativity, it's the ability to hold on to electrons. For ionization, it's the opposite of that. It's how much energy is required to take it away. And so, both electronegativity and the atom size play a really big role into determining how much energy it takes to remove an electron. Because what's going on here is that if an atom is very electronegative, then it takes a lot of energy to get rid of the ionization energy. Because its electronegativity is so strong, it's not likely to give it up. So you need to put in a lot of energy for that. And then what we see with the atom size, if we zoom into this picture, notice the distance that we go for our valence electrons. These are the electrons that will be removed first because they're the easiest to get to. They're the farthest on the outside. And so when we start with lithium, notice that it will have an ionization energy of 526 kilojoules. Don't worry about what the range of this is. Just focus on the number for now. But notice that we're only 1 and 2 levels out from the nucleus when we're dealing with the valence electrons of lithium. As opposed to sodium, we would have to go from the nucleus 1, 2, and 3 levels out, and we get an ionization energy of 502. That's slower than the 526 because this electron in the 3rd energy level is farther away than this one in the second energy level. So the bigger our atoms get, the farther and farther that those valence electrons get from the nucleus, and the more difficult it is for the nucleus to hold on to its electrons. That's why when we move on to potassium, again, we're looking at 1, 2, 3, 4 layers out from the nucleus. And so that's the farthest that we've seen so far, and it will also have the lowest ionization energy of these three. And so the more layers that we add, the more difficult it will be for atoms to hold on to their nucleus. So for this reason, helium will have the highest ionization energy. And so remember, helium is over here in the top right. And so it will, it has the smallest atom and the least number of energy levels. So that's why it's very easy for its nucleus to hold on to the electrons. Whereas you compare it with francium, then it has the lowest energy required to take away an electron, because francium is even bigger than the cesium atom on my graphic. So those valence electrons are very far away from the nucleus, so it's very easy to take them away. And then to add to that, francium is just not a very electronegative element. It's the least electronegative, so it doesn't have the strength to hold on to an electron, and then those electrons are very far away, so it's even harder to keep hold of them. So we can use a similar trend if you're comparing ionization energies of two different elements. The higher it is on the periodic table, then the stronger its ionization energy will be, the higher the energy will be. And as it moves over to the right, the ones closest to the right side, they will need the highest energy to remove them. And so we can again draw our arrow going from francium all the way to helium. And so anytime you're moving towards helium on the periodic table, that means that you will require more energy to remove an electron. Now notice something interesting, that this graphic here for electronegativity and my graphic for ionization energy, that they follow the same pattern. It's the same trend. And so just this makes it a little bit easier on us that two of these trends follow the same pattern, or I should say two of these properties follow the same trend. Where anytime you're moving towards the top right side of the periodic table, you're increasing the electronegativity, and you're also increasing the ionization energy. And then the atomic radii, the size for atoms, it will follow the opposite trend, where as we move towards the bottom left, we're increasing the atomic size. All right, and so that does it. Everything for that we need to talk about the periodic table, how to read it, and all the information that is packed into this simple-looking list of elements. So after this, I hope that you're more able to pick up on different information on different elements, what some of their different properties are, because we'll be using a lot of those properties to predict what their reactivity and their properties, or chemical properties, will be in the next chapter when we talk about chemical bonding.